Structure and character of a near-field RFID antenna. The current distribution of the near-field antenna is in phase. That is, the current on the loops has the same orientation. For example, a two-layer and open-circuit shape near-field antenna made by PCB board is shown in Figure 1. The current character is explained by this example. Model and structure of the proposed antenna: A. 3D view, B. Top view and C. Side view. Figure 1a shows the structure of the antenna, which is composed of two PCB layers. The top layer is mainly composed of two quasi-half loops which are connected with two folded straight terminals. The bottom layer is feed network with ground and lead are printed onto top and bottom surface, respectively. Fed at edge of bottom layer, 50 ohm microstrip line is connected with two 100 ohm lines, which are connected to two metal columns in another end. The other end of each column is connected to metal quasi-half loop strip. There are four loads on two quasi-half loops which are marked by 1, 2, 3 and 4 in Figure 1a. The two PCB boards are connected by two metal columns and fixed by two nylon columns. Figure 1b shows the top view. Angle and radius of loop are marked by fine Ren, respectively. Length of folded terminal, width of metal strip and radius of PCB board are marked by L, wand route, respectively. The value of loads 1, 3 is Res 1 and 2, 4 is Res 2. Figure 1c shows the side view. The distance between two PCB layers and thickness of top PCB board are marked by hand T, respectively. Bottom layer has the same size and material as top layer. Performance of the antenna. The proposed antenna can be printed onto any substrate and optimized at specific operating frequency by properly selecting the geometrical parameters. The antenna prototype is printed onto a FR4 substrate, epsilon r equals 4.4, 10 delta equals 0.02, thickness T equals 2 mm. The optimized antenna has parameters of H equals 15 mm, W equals 2 mm, RIN equals 25 mm, route equals 34 mm, Res 1 equals 30 ohm, Res 2 equals 50 ohm, L equals 8 mm and T equals 2 mm. As shown in Figure 2a and b, the antenna is fed by SMA port on the edge of the bottom layer. The new proposed antenna has many advantages such as strong magnetic field, low far-field gain, wide bandwidth, small size and so on. Photograph of the antenna, a 45 degrees view of the antenna and b, bottom view of the antenna. The impedance matching measurement of the antennas was carried out using the Agilent N5230A vector network analyzer. Figure 3 shows the simulated and measured return loss. The proposed antenna exhibits broadband impedance bandwidth. The frequency range for -15 dB return loss is from 826 to 950 MHz or 124 MHz bandwidth. The measured result agrees well with the simulation. S11 of the actual antenna and simulation model. The far-field gain and directivity are shown in Figure 4. It is clear that the gain is lower than -10 dB at any direction and about 15 dB lower than directivity. A. Far-field gain versus theta at different phi, which is 0, 90, 180 and 270 degrees, and marked by 4 curves. B. Directivity versus theta at different phi, which is same as A. Figure 5 shows the current distribution of different phases. Different from conventional traveling wave antenna, current on the loop assumes standing wave distribution. One important factor of current is in phase. Because magnetic field produced by the currents on the adjacent sides of the antenna cancel out each other and is thus very weak in the central portion of interrogation zone if the current distribution is out phase. In Figure 5, current of this antenna is not out phase because of small electrical length of the quasi-half loop. At the phases of 45, 90 and 135 degree, the currents are all strong. Actually, the magnetic field at these phases are also strong. The result could be verified by the comparison between Figures 5 and 6. Current distribution on metal strip at different phases, A 0 degrees, B 45 degrees, C 90 degrees and D 135 degrees. Different phases offs orientation magnetic field distribution on the reference plane, which is 1 cm above the top of antenna, A 0 degrees, B 45 degrees, C 90 degrees and d 135 degrees. Figure 6 shows that magnetic field is concentrated and uniform around the center region of antenna at different phases, 0 degrees, 45 degrees, 90 degrees, 135 degrees. Moreover, as a result of folded terminal, average current can be enhanced on the outer loop so that strong magnetic field intensity is obtained. Figure 7a shows the magnetic field distribution at difference above the surface of antenna's top. The reason for choosing such a graduation scale is narrowly related with reading tag ability, which will be discussed later. Figure 7b focuses on the magnetic field intensity attenuation versus z-axis. Simulated magnetic field distribution of the antenna operated at 868 MHz, a z-orientation magnetic field distribution at difference. Radius of reference plane is also 50 mm and, b, magnetic field intensity of the antennas along axis. Compared to other antenna, it could be found that the z-orientation magnetic field of the new antenna is much stronger. For example, referred by figure 7b, the magnetic field of this antenna is significantly stronger than that of the proposed traveling wave antenna in that same z. At z equals 2 cm, 2-layer and 2 quasi-half loops antenna has magnetic field intensity of -3 dB/m, whereas the antenna from has only -15 dB/m. Taking figure 7a as a reference, the magnetic field in center region of the antenna is also stronger than the another broadband antenna which is proposed by Ching et al. It shows that magnetic field of the antenna from is lower than -10 dB/m at z equals half a millimeter, whereas 2-layer and 2 quasi-half loops antenna is stronger than 0 dB/m although at z equals 1 cm.